Let's talk about how we can use angle-angle, side-side-side, or side-angle-side similarity theorems to prove that triangles in the coordinate plane are similar. For example, how could we prove that these two triangles are similar? Well, they look pretty similar, so they must be similar, right? Well, we have to prove it. We have to actually show why we think these are or are not similar. One of the ways that you can prove that triangles in the coordinate plane are similar is by calculating their side lengths with the distance formula, and then showing that their side lengths are proportional. In order to use the distance formula, the first thing you need are the coordinates, so I'm just going to jot down each of the coordinates of my points real quick so I can use them to fill in my formula. The good news is, though, that we don't actually have to calculate all 6 of those side lengths. 2 of them are horizontal or vertical lines, which means I can just count. So QR is 1, 2, 3, 4, 5, 6 units, and YZ is 1, 2, 3, 4, 5, 6, 7, 8 units. These two segments I can count the lengths of because they're horizontal or vertical. I can't count the length of diagonal segments. So that's what the distance formula is for. If I wanted to calculate the length of PQ, I would be using the point 1, 4 and negative 9, 8 and plugging those numbers into the distance formula. So I would say x2 minus x1, that's negative 9 minus 1 squared, plus y2 minus y1 squared, that's 8 minus 4 squared, and a big old square root over top of it. Underneath of that radical, it simplifies to 116. The simplified radical form would be 2 root 29 units, or the decimal approximation would be 10.77. And you would follow the same process to calculate the lengths of PR and XY and XZ. I'm not going to walk you through all that because by now you know how to use the distance formula. If you don't, there's a link to my distance formula video in the card. So now that I know the lengths of all 6 sides, 3 for triangle PQR and 3 sides for triangle XYZ, I'm going to set up a statement of proportionality comparing each of those side lengths, and then I'll plug in each of the lengths that I calculated. Now you could either use the simplified radical forms, or you could use the decimal approximations. Technically, the simplified radical form is more exact, so it's a better way to go about it. But since our next step is to simplify these fractions, and they're so ugly, whether they have radicals in them or decimals in them, they're such ugly fractions to try to reduce, I'm not actually going to try to reduce the fractions the way that 6/8 reduces to 3/4. I really can't do that with the rest of these fractions. So instead, I'm just going to divide. 6 divided by 8 is 0.75. These two numbers divide to about 0.824, and these two numbers divide to about 0.828. Looking at these 3 answers, they're not the same thing, which means that the side lengths are not proportional. And that means that those two triangles are not similar. They might have looked similar, but we have proven that based on their side lengths, they are not similar. What about our next example? Do you think we have to use the distance formula here, or do you think there's another way? For example, I see a vertical line and a horizontal line. That means that DE is perpendicular to AC. And if they're perpendicular, then they're both right angles. And if they're right angles, then they're congruent to each other. Alternatively, you could have said that they're vertical angles, and therefore they're congruent to each other. Either way, you would be making the same conclusion that angle ABD is congruent to angle CBE. So that's one pair of corresponding angles that's congruent. I either need another pair of corresponding angles that are congruent, or I need to show that the sides that create those angles are proportional. Well, the sides that created these angles are horizontal and vertical lines. They're really easy to count the lengths of. AB is 5 units, DB is 3 units, and EB is 6 units, CB is 10 units. So if I could show that these lengths are proportional, then I would be able to say that the triangles are similar. So let's set up some ratios. AB over DB equals CB over EB. Well, 10/6, that's easy enough to reduce. It reduces to 5/3, which is the same thing as the ratio of AB over DB. So since these two pairs of corresponding sides reduce to the same scale factor, that's enough information to say that these two triangles are similar. Don't forget to make sure that your letters go in a corresponding order. If I go from A to B to D for the first triangle's name, which again you get to pick whatever order you want to call the first one, that's totally up to you. But once you have that established, the other triangle's name has to go in the same order. So here I'm basically going from the smaller acute angle to the right angle to the bigger acute angle. So I have to go in the same order when I name my yellow triangle. So smaller acute angle to right angle to bigger acute angle. It has to be CBE. What about this last diagram? We could certainly use the distance formula to calculate the lengths of FG and FI and FH and FJ and GH and IJ. That's certainly one way to go about it. But that seems like a lot of work. Instead, what if we tried to use angle-angle similarity? Well, we definitely know that angle F is congruent to angle F by the reflexive property. But that's not enough, right? That's only one angle. We need to have two pairs of corresponding angles that are congruent. If I could show that IJ was parallel to GH, then I could use corresponding angles to prove that I had some more congruent angles in this diagram. Well, remember that in the coordinate plane, two lines are parallel if they have the same slope. So let's just count the slopes of IJ and GH. Alternatively, feel free to use the slope formula. The slope of IJ, well, I go down 2, 1, 2, and to the right, 1, 2, 3, 4, 5, 6, 7, 8. So that slope reduces to negative 1/4. Let's calculate the slope of GH. I go down 1, 2, 3, 4, 5, and I go to the right 20. And negative 5/20 also reduces to negative 1/4. So since the slopes of these two lines are equal, the lines must be parallel. And since the lines are parallel, we can conclude that angle FIJ, this angle right here, is congruent to angle FGH, or just angle G. This angle right here. These two angles are corresponding angles, which means they have to be congruent. So you could combine that with angle F being congruent to angle F by the reflexive property, like we said earlier, or you could also say that angle FJI is congruent to angle FHG by the corresponding angles postulate as well. So we actually have enough information in this diagram to prove that not only two pairs of corresponding angles are congruent, but actually all three pairs of corresponding angles are congruent. So that's more than enough information to show that triangle FIJ is similar to triangle FGH by angle-angle similarity. And that's all you need to know about proving that triangles are similar if they're graphed in the coordinate plane. In the next part of this lesson, we're going to explore how to write a two-column proof to show that two triangles are similar.